Thank you. It's a pleasure to be here to give this presentation on mixing. Let me tell you briefly about myself. I manage engineering for Lanza. I've been working for Lanza and the legacy companies for almost 38 years. So I know a little bit about wood treating and a little bit about wood treating plants. I'm a civil engineer by training. I've got a bachelor's degree from the University of Delaware. Yes, I'm a Yankee. I'm a blue hen. Who knows about blue hen? You do, okay. Don't cook us, okay? You're going to smoke the hens, that's right.
Smoke it won't help.
I've got a master's degree in industrial engineering, and I'm licensed in 6 states. A few introductory remarks, if I could. First of all, I don't pretend to be an expert about mixing. It's obvious after joining you for the reception last night and the dinner afterwards, and watching all of you participate and enjoy yourselves, that you are really the ones that are the experts in mixing. I am an amateur bystander. But having said that, in the course of the discussion today, there's a couple things that we need to be careful of. I am going to be passing around some small agitator blades, some small pieces of equipment. These are not toys. Please be careful with them. They've been machined for test work that we do at our Conley facility. They are stainless steel. They do have sharp edges. Please don't even take one of these and pretend you're a ninja and try and throw it against the wall or something like that, okay? Be careful handling them. I want you to see them. I want you to understand what they're doing. And I've brought a variety of these to help in that understanding. Second, by training, I do not pretend, I'm going to repeat my first statement, that I'm an expert in this. I have been involved in the installation and design of a lot of agitation equipment in the past 15 years. I do not make any claims to be an expert in the field. I do claim to be a practitioner. I understand the technology. I've applied the technology. Mixing has moved from the area of art and technique and is more of a science that is well understood in the engineering disciplines. I hope to communicate that to you. And so here's what the objective of my conversation with you is this morning. It is my opinion that our industry, the wood treating industry, could benefit from doing a better job of mixing all the solutions in our tanks, whether it's concentrate, whether it's working solution, regardless of what the wood preservative system is. Or whether it's penna, creosote, CCA, copper azoles, fire retardants, organics, PTI, any of these different systems would benefit from better mixing. I can't tell you how many times I've been asked by an owner or a plant operator, Frank, if I had an opportunity to invest in my plant, where could I spend my money wisely? And my answer immediately is that I would put mixers or some form of mixing into your work tanks, into your storage tanks. I think we can all agree that if we can do a better job of maintaining the integrity of our solutions in our tanks, it will improve the results of our quality control. It will improve the results of our treating. And that has cost implications as far as the operation of the plant. It gives us a better impression with the consumers and the customers that we're serving. And I hope to lay an argument today for that. So having said that, and hopefully my little clicker is going to work here, and of course it didn't. There we go. Here's our agenda for today, or here's my agenda rather. How do we define quality mixing? I want to talk about what issues we encounter in tanks. Why do we need good mixing, and what chemistry? Some of this I've already covered in my introductory comments. I want to talk about different types of mixing equipment, and I want to try and overcome some of the assumptions, presuppositions that are associated with what's good, what's bad, and what works best. Then I'm going to go through, and I'm hoping this will be helpful because, you know, Alonza does not manufacture pen or any oil-borne wood preservatives. However, the engineering group at Alonza has worked with every preservative system that's in North America. We have an extensive background. And I've drawn on an example where we worked on a pen system to illustrate a couple of the interesting features and I want to suggest some things that you can do with mixing and with creative uses of instrumentation. And then what we're going to do is we're going to fire Junior up here, and I'll talk a little bit about what we've got here. Yes, it's water, it's not vodka, it's not margaritas, it's not anything like that. And no, we're not going to use this as the basis for creating a microbrewery. I don't know what I'm doing. All right? And anywhere in the course of the conversation, please feel free to ask any questions. And I'll be here most of the day for any questions you might have that you don't have opportunity to ask this morning. So, if any of you have ever been down to Disney World, you know about the Tower of Terror. So I've made the Tank of Terror. And I've tried to sit down and figure out how many different things can go wrong inside of a tank. And I'm not saying this is comprehensive, but it's my best shot. So we could have fallout at the bottom of the tank. We could have CCA fallout. We could have debris from pentachlorophenol systems. You know, typically your CCA fallouts because of wood sugars reacting in the tank and precipitating. As a sidebar, CCA treaters, how much initial vacuum, what's the lowest amount of initial vacuum you should ever pull to prevent CCA fallout in the tanks? Anybody know? Nobody's raised their hand. Either you don't know or you're shy. I'm going to tell you, don't go below 18 inches of initial vacuum. Don't go below that. If you do, you're asking for trouble with round stock. 15 inches tends to be the threshold with dimensional lumber. Precipitation exists in the bottom of the tank because the system is idle. Now, I know we talk about, historically, we've always been worked under the impression that the turbulence associated with flow, filling and emptying the treating cylinder, is sufficient to keep everything suspended. And that is true to an extent. But with the round stock systems in particular, where you've got 10-inch, 12-inch lines and moving solution 4 to 6,000 gallons a minute, into a tank that's got 50,000 gallons, you're not turning things over enough to keep everything mixed up. And the fact of the matter is that when we fill the cylinder, even at those flow rates, basically once the cylinder is full, what's in the cylinder is static and idle, if you think about it. Every one of the competitors seems to control pressure in the cylinder during the pressure step a little differently. Some people like to deadhead the pressure. We have a tendency to have a control valve and flow things through. So I'm getting some movement through the treating cylinder, which is by design. But even that, I'm only probably moving 200 to 300 gallons a minute. So there's not enough turnover in the process of filling and emptying the cylinder to keep anything that is falling out in the bottom of the tank from really getting stirred up and keeping it in solution. That's a problem. Because long term, at some point, you're going to have to empty this tank, and when you do, you're going to be cleaning that out. I don't need to talk to any of you about the costs of cleanup. I think you're all completely aware of that. The other thing that we see in the tanks, and this is more unique to oil-borne systems, is you're going to get chemical and you're going to get thermal layering. As your feedstocks, as your carriers are coming from different sources, they're going to have different properties. And you really can't effectively blend them in the process of filling the tank back up after you treat so many charges. It just doesn't work that way. Those different carriers are going to separate. They're going to float on top of one another. They're not even the turbulence associated with filling and emptying the cylinder. It's going to take a long time moving that solution back and forth to try and get it homogeneous. Then, as some of you are aware, the copper azole systems have floating components. Now, I know that of late, we and the competitors have started fielding systems that have suspending agents in them to keep that from happening. But initially, when we put copper azole in the field, within minutes, the azole system would float to the top. You can't resuspend something on the top of a tank with a pump recirculation system. It doesn't work that way. So that's a problem. Then, all the new wood treating systems, and I'm not talking about the ones we're currently working with, but all those in development. I like to describe them as finesse systems that are made up of squishes and squirts. You know, they have mold inhibitors, they have corrosion inhibitors, they have defoamers, and we're adding them in very, very small quantities. So we add these things in small quantities into a 20 to 30,000 gallon tank. We say it's adequate, and then like we've done for the past, 90 years, we send the operator out, have him take a sample out of a 1/4-inch sample port, and say that sample is representative of the tank. Now, everyone in this room knows that that is not a true statement, but we really have not had anything else to work with. So these are some of the problems that lack of homogeneity manifests itself when you have a tank that's got either small quantities, floating components, separation due to either different properties, or the fallout, precipitation at the bottom. These are all things that all of you are familiar with. And the argument I'm trying to make is that if we can overcome this, if we can overcome the issues with these tanks, if we can make the contents homogeneous, we're going to do a better job treating, we're going to do a better job with our cost control, and quality control is going to be easier. So why do we need good mixing? We need good mixing to maintain the integrity of our treating solutions. The current family of finesse wood preservatives, they are not true solutions. CCA is a true solution, believe it or not. Thick as it is, it's a true solution. But all the new systems are not true solutions, and they require agitation to keep them together. It's kind of like baking a cake, to be truthful with you. You add all the components in the mixer, you turn it on, stirs it up, you come out with something good. We need to improve the quality of our treating. I'm fully convinced that if we were to apply the technology I'm talking about to historical Finesse systems, creosote systems, copper naphthalene, it doesn't matter what it is, it would improve the quality of our treating. We need to control solid formation and settlement. Most of you are dealing with round stock, and I don't need to tell you about what is brought into your treating systems from round stock laying in the yard. You got wood fiber, you got chips, you got sand, dust, dirt. All those things are being taken into the system, despite your best efforts, and I think that some of the measures I've seen are very heroic. But to the extent that they precipitate and fall on the bottom, you wind up paying the price long term and the cost of generation of hazardous waste. A lesser known and understood benefit of good mixing is controlling the temperature in the tank. Some of you are aware of the fact, maybe you're not, that at one time we had a process patent for making water cold. Now you would think that's kind of strange, but that's how the chiller patent came into existence, where we use mechanical cooling to control the reaction for CCA and keep it from precipitating in the tank. A key element to doing that is mechanical agitation. Now, how do we define good mixing? I think everyone understands this too. Good mixing can be defined as achieving homogeneity. In other words, what we want in a tank is similar properties from top to bottom, everywhere. And we can use the number of times we turn a tank over. Turnover is the criteria for the quality of our mixing. In other words, the more times we turn a tank over, the more confidence we have that we've achieved homogeneity. The real problem is that with different types of equipment, we don't have the time in the normal course of treating to turn the tank over enough to achieve a level of homogeneity so that we can say with confidence, when we take the sample out of the 1/4-inch sample port, that this is representative of what's in the tank. And I've already said, what chemical systems benefit from good mixing? All of them do. So let's take a look. I'm going to show you some different types of tank mixing technology, and I've worked with all of these. The first one is air agitation. And by that, I'm not talking about sparging large volumes of air bubbles into a tank. There are a lot of older wood treating plants that I've been to where they'll put a ring into the bottom of the tank and they'll just blow an enormous amount of air into the tank in a hopes and an attempt and a hope that it will help get some motion moving in the tank, create a pattern, and stir everything up. I'm here to tell you that that does not work. What does work is technology that was developed in the oil fields where you install a series of large diameter plates, 1 foot to 2 foot in diameter, depending on the tank size, in a pattern in the bottom of the tank, and you use air and form large air bubbles. Now, these bubbles are 1 foot to 2 foot in diameter. If you sequence the pattern correctly, it will mix the tank up. It'll mix the tank up. The upside is that the technology does work to some extent. It requires extensive internal piping because, as you can imagine, you've got to run some 2-inch lines from the top of your tank all the way to the bottom of these plates where these bubbles are being formed. Areas of concern. I don't know whether all of you are aware what the standards are for the tanks we're using, but they're all basically designed API 650, which is a 1 atmosphere tank. So it frightens me a little bit to be blowing air bubbles into a tank and having the possibility that the top of the tank where the vent's supposed to be to get sealed off. That would be an unpleasant situation. So I've never really embraced this. The other issues is that anytime we're blowing air through a wood preservative, there may be some oxidation of the dispersing agents, there may be air emission and worker exposure issues, and you would have to do an explicit evaluation of the size of the air receiver and the compressor you would need, because the volume of air you're blowing into this tank with these large bubbles is enormous. And you've got the air compressor running all the time. What's more common is pump recirculation. And as I've shown in my drawing here, we're taking a pump, sucking out of the bottom at a single point, discharging at the top, and turning this over. And there's a lot of folks that do this. Pump recirculation, and I've got an impeller here I'm going to show you. The pumps are normally operating at one of the 4 synchronous speeds that are associated with 60 hertz equipment in the United States. 900 RPM, 1200 RPM, 1800 RPM, 3600 RPM. And centrifugal pumps are very good for creating pressure and moving solutions at ranges of gallons per minute up to about 2,000 to 3,000 gallons a minute. So I want you all to do the very sophisticated engineering math. If I've got a 50,000 gallon tank and I'm circulating at 2,500 gallons a minute, how long is it going to take for me to turn that tank over one time? 20 minutes, right? It's a long time. Long time. And the truth of the matter is that you don't even have a good feeling whether you're getting all of the contents of the tank being completely circulated, right? Because it's a point suction and a point discharge. There's another downside. This is an open impeller. It's been trimmed to about 9 inches. If this is turning at 900 to 3,600 RPM, what do you think it's doing to the treating solution? It's shearing it. I participated in the first trials of our ET solution at a plant that I won't name for you. And we were having difficulty with ET initially because it was just too thick. We needed to shear it. We brought in some commercial shearing equipment, and it wasn't sufficient. So we went back to Conley where we store equipment. We brought a 100 horsepower, 4-inch suction, 3-inch discharge, 9-inch impeller, centrifugal pump. And I guarantee you, it tore the solution apart in no time. So it's good for that. But it took forever because the tank was 30,000 gallons. So Just think about that. You've got a pump impeller versus a little agitator blade, okay? I'll pass this around. Be careful, this has got some sharp edges on it. I just want you to look at it, get a feel for it. A couple of notes about pumps. Now, I've worked with a lot of centrifugal and different types of pumps. You're going to have a basket strainer in it. We've already talked about precipitation forming in the bottom of the tanks. And you're going to have a basket strainer on this piece of equipment to keep them from jamming the pump up. Now, that particular blade that is being passed around will pass quarter-inch solids, but we all know at a pole plant, a kiln operation, you're going to have large pieces of debris. So your operator's going to be going out there, and he's going to be having to change that, clean that basket strainer out, and mill it all the time. The other side is that every 16,000 hours of operation, you're going to be changing the mechanical seal in that pump. That's a rough number. For those of you that are working mechanical equipment, 16,000 hours, it's about 2.5 years of operation. Pretty good service for a mechanical seal. So I want to show you a different technique using a centrifugal pump. You can pass one of these around. I don't know if you've ever seen this. This is a tank mixing eductor. These happen to be plastic. They're 1.5 inch diameter. And if you recall high school chemistry, when you needed to pull a suction on some of your test tubes or lab equipment, you would turn on the faucet, there'd be a little rubber hose with a little fixture on it. This is the same thing. It's a venturi. As this passes around, I'll pass this one around as well. You take your discharge of your pump into the back end, and you'll notice there's a nozzle here. And what the nozzle will do is, because it's creating a low point, a low pressure point here, kind of like the lift effect on an airplane wing, what will happen is it will draw solution through the open louvers on the 4 sides, and it will magnify the discharge a factor of 2, 3, or 4. Okay? Let me pass this around. I've got 2 of them. The plastic ones are fairly inexpensive, and they get kind of pricey as you get up in size. I've seen these, we've employed these in a variety of different ways. The best way to do it, and I call this a poor man's mixer, is what I call this, is to create a pattern in the tank. You'll notice this drawing here I'm pointing to has 5 tank mixing inductors on it. One of these should be pointed to the floor. And the reason for that is we call that the sweeper. Because I'm going to make the assumption that even with this tank mixing inductor, which you're going to operate not continuously, but periodically, you want to be able to get any solids that have precipitated resuspended. So you have the sweeper going to the floor, and then what you have to do is you point the other eductors upwards. Now, having said that, there's a little engineering required with this, because depending on the height of your tank, you have to design the number and size of the eductors, taking in consideration the size of the discharge plume and how far out it's going to go. In other words, if I put one gigantic eductor on a really small pump, I'm not going to get a lot of mixing, and it's not going to go very far. However, if I have smaller eductors, these are 1.5 inches that are going around the room here, and I size them with a pump that gives me enough discharge pressure, I enjoy the benefits of multiplication coming out of the nozzle itself, 2 to 3, plus the discharge plume will be long enough so that I can get to the upper reaches of the tank. It's a little bit of a finesse. It's not difficult, but you can't just buy the piece of equipment, stick it in, and make the assumption that it's going to work. And here's a picture. Don't ask me how I got the picture, okay? Don't ask, all right? This is someone's attempt to try and make a little patterned eductor. This has got 4. You see the one pointing downward. It actually got 2 and 2 up. And it was just a quick way of trying to install them in the tank. It's a waterborne tank, by the way. And then that brings me to turbine mixers. And I've probably installed, close to 300 of these pieces of equipment. And people seem to be, think that they're burdensome as far as the cost of installation and the operating costs. I'm here to tell you that that is just not true. This piece of equipment is low horsepower. It typically turns, and this is what I wanted to impress upon you, 40 to 70 RPM. So if you remember that impeller that's going around here, remember I said that a centrifugal pump is going to operate at one of the 4 synchronous speeds. It's going to operate at 900, 1200, 1800, or 3600 RPM. Typically, your agitators, your turbine mixers are only turning 40 to 70 RPM. And I'm going to work through some examples with you to give you an idea of what the pumping capacity of this equipment is. The operating costs for a piece of equipment like this are typically $480 per horsepower per year. So if you've got a 2 horsepower mixer, it's costing you $1,000 a year to operate it. Now, I don't know about you, but I'm going to make the assumption that all of you have the best treating plant managers and operators, and you never have a problem, and your forklift and lift operators don't ever bang into building columns, and they don't ever tear equipment up, and they don't intentionally walk away from maintenance procedures, and they let vacuum pumps run dry, and they don't ever do any of those things, right? Your guys never do any of that sort of stuff. I know that. I've been there. Well, what I love about this piece of equipment is that, first of all, it's mounted on the top of the tank, so they can't get at it. Okay? They can't get at it to hurt. And the second thing is that the maintenance on this, you change the oil in the gearbox once a year, and you forget it. And it runs all the time. You don't ever turn it off. You turn it on, you let it run. It just runs. The shafts are typically 2.5 to 3 inches in diameter, and then we have an impeller that's 30 inches to 50 inches in diameter. And I'm going to show you one example here of a couple agitator applications. These pieces of equipment create up, down, circular, and complex motions, and they do that with a combination of the size and shape of the agitator blades. You see the one in my left hand here has 4, and I'm going to pass this around. Be careful when you hold it, okay? This blade is a pitched blade. In other words, you can see as I'm holding it here, the angle of the blade is at 45 degrees. This blade, in contrast, is a high efficiency impeller, and it has a little bit of curvature to the blade. The one I have in the tank here is a 10-inch blade. I'll pass these around. Be careful.
So I'm not allowed to throw these at anybody?
Don't throw them at anyone. Don't use them to, cook them in your smoker or anything like that.
Time to get your airflow.
The agitators work by as I said, a combination of the shape of the blade, the speed, the diameter, and it depends on the geometry of the tank. Okay. So we design these mixers for different applications, and this is a graphic rendering of the output of computational fluid analysis. This is an off-center design. In other words, you'll notice that the center line of the agitator is not in the center of the tank. What would happen if I took an agitator and put it into the center of the tank without any sort of internal structures? Does anyone have an idea? What would happen?
Create a vortex.
I'm sorry?
That you create a vortex.
You're absolutely correct. You would get the entire mass of the liquid moving all at once, and you wouldn't get good mixing. So as a consequence, and an accommodation, on new tanks, we will mount the agitator in the center of the tank as this one. And you can look inside the tank. I've got baffles every 120 degrees in here. It's just a plate projection. Its size, the plate projection is a characteristic of the diameter and the height of the tank, okay? But as I was mentioning initially, you know, agitation has moved out of the realm of art and technique and is really in the realm of engineering science. What the motions, the applications are very well understood anymore. So I'm going to show you an analysis. This is a vector analysis showing up, down, and outward movement of an off-center agitator design. Here's a photograph of one that we took. You can see the agitator support structure, agitator mounted on it. Let's just hope this thing works here. How do you find my mouse? There it is. Okay, this is a vector representation of the flow of an off-center agitator in a tank. The scale on the left side of the screen as you're looking at it indicates the intensity and is representative of the amount of energy that the agitator is putting into the tank. In other words, you'll see on the exterior of the blade how red it is. That's where most of the work is being done. In this case, it's difficult for you to see from where you're sitting, but all the little blue dots here are actually vector arrows showing that the motion is down, then out, and then up the side of the tank. Let me make sure everyone understands something about agitators, because I run into a common misconception all the time. When you're installing an agitator in a tank, it does not suck up. It pushes down. And what it does is the motion is rather complex. It shoves down from the top, goes out, goes up to the top of the tank, and envelops it like this. And that's why you can use an agitator, mechanical agitation, to suspend everything and anything in a tank. It doesn't matter whether it's floating on the top. It's going to get sucked down because of the force of the blade. Typically, this piece of equipment is only turning 45 RPM. And because it's turning so slowly, it is a low shear piece of equipment. So it won't tear up water repellents. It won't tear up oil-borne solutions. It won't tear up anything that's fragile in the way of a solution. Just as a kudo, I got this. I do most of my agitator work with Cheminir, where they have a mixer specialist, and he helped me with these designs.
What about the formation of emulsions in oil systems where you have water present?
It'll mix them all up. It won't tear them up. It'll mix them all up. It's a good question. That was a vector representation. I'm going to show you a raster representation. And this one is a little bit interesting if I can get this working here.
Is that the Jamaican version?
No, it's not the Jamaican version. All right. This is a raster representation of a tank with two mixers in it. And the reason I asked them to put this together for me is because in a tall tank, one agitator blade is not sufficient. You may have two, you may have three. This one has two, and what I need you to look at here, you can see the intensity of the agitation by the color scheme again. And as you watch this over time lapse, you'll notice that the liquid that's being pumped, and let's use that word, from the top mixer, is making its way down to the bottom mixer, where again, you'll see the outward motion here where it's coming to the top. Can everybody see that? You know, those of you in the back of the room, let me know you're alive. Okay, good. Thank you. This again is an off-center design. Off-center designs are designs that we use in tanks that are already existing in the field, where we don't want to go to the time and the expense of installing baffles in a tank. That would be an expensive an unnecessary expenditure. The downside of having off-center design is that you don't, are the following things. The mixing isn't quite as good as it could be. And the equipment is a little more expensive because we've got to put more energy into an off-center design agitator for it to achieve the level of homogeneity that we're able to achieve with the center baffle design. So this pattern here is a little bit different. This was designed for a pumping rate in excess of 12,000 gallons a minute, and this mixer is turning at 50 RPM. You can see the agitators are both mounted in the center of the tank now. You see there's symmetry in the pumping action. Again, what I want you to watch, and I'll make sure I get out of the way, is that eventually the liquid that's being pumped from the top blade will make it to the bottom, and you're going to see complete up-down motion. You see it here on the left side there where it has already made contact with the lower blade. Everybody, can everybody see this? Everybody, okay?
Frank, you said a tall tank. What's your definition of a tall tank?
You know, we've agitated tanks that are 35, 40 feet tall, okay? The problem with a tall tank, and we've, you know, all the pole plants, you know, Ron, your plant, they have tall tanks. Where you get into a little bit of trouble is if the height to diameter gets really large. In other words, an 8-foot diameter tank that's 30 foot tall becomes a little bit of a challenge. It becomes a challenge because the equipment's going to get expensive. The shaft on that may be 4 inches in diameter. Big shaft, okay? Okay. All right, so let's look at some applications, okay? The first one I would like to show you is a simple suspension of an MCA concentrate tank. It's a vertical upright tank. It's not very tall. It's only 15 foot tall, 12 foot diameter. I get from the manufacturer computational fluid dynamics analysis. This mixer is going to have 2 blades, and it's going to have a 3 horsepower mixer. It's going to be turning 56 RPM. The diameter of the impeller is 46 inches. I'm 6 foot tall, they're 6 foot. So it's smaller than my wingspan. Here's what's interesting. The pumping rate of this piece of equipment is 16,000 gallons a minute. 16,000 gallons a minute. They estimate the blend time to 100% homogeneity, 58 seconds. That's with a piece of equipment that's only 3 horsepower. I could not achieve that with any of the other technologies I showed you before. It's not possible. Here's what the mixer looks like in design profile. We can get a variety of different gearboxes depending on what our clearance is. This one happens to be a right angle. Again, the maintenance on this is that once a year you go change your oil in it. It's on top of the tank. They can't get to it. So they can't destroy it. This one here I hope you find interesting. This is a heat exchange application. It's a CCA work tank, and Ron, you were talking about big ones. This one's 35 feet tall. This tank's 24 foot in diameter. This is a big tank. We have a chiller system on it. I'll show you the design, okay? It has, the design volume is 111,000 gallons. This is a big tank. It's got a 102-inch diameter impeller. 102 inch. There's, okay? It's a lot bigger than I am in wingspan. The mixer is only turning 25 RPM. It's only 5 horsepower. The pumping rate is 59,000 gallons a minute. And the blend time to 100% homogeneity from top to bottom is 13 minutes. See, now that's moving fast enough where it can keep up with production. You can't change a pull charge out that fast, right? So what does it look like? Oh, my drawing didn't come out too well. It's Offcenter Design. I apologize. It's Offcenter Agitator Design. And then on the side here, we have submerged platens in the tank. This is similar on to what you've got. And we're just running chilled water through them. We're taking advantage of the angled orientation inside the tank so that the platens act as baffles. They interrupt the flow so we don't get the vortexing effect that you were talking about. The baffles actually work doubly. The reason that this is so effective is that you're getting good mixing in the tank, so you're mixing at 111,000 gallons, and you're getting enough turbulence by the plates on both sides. You know, we're probably running 45-degree water through there. That's what you're going to get out of the chiller. Okay, I brought this one for those of you that are trimming pen. I'll throw some ideas at you. Okay. This is a solid suspension application. It's a pen work tank. It's horizontal. I intentionally chose a tank with different geometry because everything I've been showing so far are vertical tanks with they're uniform in size and dimension, but they're pretty standard. Interestingly enough, mechanical agitators work very well with tanks of odd geometry, rectangular, square, or even horizontal tanks. The way that they accommodate them and modify the design is they will speed the agitator up a little bit to get more flow, and I'm going to show that to you. So in this case here, we had layering in the tank because of different feedstocks, and we had fallout in the tank. We all know where that came from. That's the problem, right? Getting fallout in the tank. So we put two 5-horsepower mixers on it. They were each pumping 34,000 gallons a minute. The blend time was 320 seconds. Here's what the agitator looked like. This agitator is turning 68 RPM. Had a 61-inch diameter impeller. We equipped it with a companion flange, so we did some specific analysis to put a pad plate on the tank with an 8-inch raised face flange. The agitator just bolted right to it. It's a standard off-center gearbox. The motor is not in the center line. This is the way they traditionally are built. And the mixer speed was 68 RPM. Here's a computational fluid dynamics of two counter-rotating mixers. So what this is doing when it's in operation is moving like this. It took me a year to figure out how to do this. They're moving opposite one another. So what's happening is that the solution at the top is coming down to the bottom. I'm sorry, it's going the other direction. Coming down through the blade, coming up to the top. And here's what's key. You see in the middle here where they're joining together? So we've positioned the mixer specifically to accomplish this. Now, here's what the mixer is going to do. Ron, here you go. The mixers are going to suspend all the solids in the tank and keep them suspended. So where are the solids going to go when you treat? Penetrators. Where are they going to go? They're going to go out in the wood. We're going out in the wood. You're getting different feedstocks. Now we're going to make everything 100% homogeneous in the tank. So if you get fuel oil from this carrier, you get fuel oil from that carrier, we're going to blend them. Now here's the interesting thing. With the tank completely homogeneous, I can take a side stream off of it. Take a little 2-inch line into a little 1-inch diameter pump. Put a basket filter in front of it, capture any solids, and then run it through a device that looks like this. This is a Coriolis meter. It's a little different it's a little different type of metering technology than anything you've ever seen. It's not a turbine meter, it's not a paddle wheel meter, it's not a mag meter. This device will measure flow, temperature, and density. If I've got temperature and density, I can calculate specific gravity. If I have the assumption of complete homogeneity in the tank, I can take my side stream, run it through the Coriolis meter, calculate specific gravity, have that input your control system. So that when your operator is doing his mixing calculations for panel, which are based on specific gravity, he's getting an updated number all the time. This is about a $15,000 instrument. I was going to bring one. We're a Rosemount shop, and Rosemount has a sister division called Micromotion that makes the Coriolis meters. And I asked the rep, I said, look, can I borrow a Coriolis meeting? I have this real important meeting I want to come to. He said, I'll be glad to come with it. I said, no, we're not going to have you come here and peddle Coriolis meters. Okay? They're about $15,000. Okay? Just think about that. Interesting application for an agitator. Now, before a system is installed in the field, in any of those applications, we test it in the lab. We have the ability, I have a picture here, this little unit here has a twin. I have a different apparatus, motor apparatus with a gearbox on it, and I have a stainless steel tank. So what we can actually do, is do scale-up work. If we come up with a difficult situation in the field, where we've got viscous material, or we've got small quantities, little bitty things, and we want to see if it's working, we can set up the small unit, take the information from the lab. I can back calculate the type of blade, the speed I need to run it, how many blades, put it in the small unit. I'm going to come pretty close to what the large unit is. And then we've gone so far, it's a fair question to ask, well, Frank, how do you know this equipment does what you're talking about? We've actually gone out in the field, climbed on top of tanks, and we've taken measurements of all the components in the tank at different portions of a treating cycle and mixing cycle, send them back to the lab, and verified how effective this technology is. With all the new Finesse chemical systems, the agitator will completely suspend microcopper azole on the work tank, and all the mold inhibitors, and the defoamer, and the water repellent in a space of less than 180 seconds, from top to bottom. We've measured it. Okay, so seems believing. So what I've got here, it's water, okay? I have a 3-sided impeller, a high efficiency impeller, and I have a 480 volt drive that's powered by 110 volt. I'll let you guys think about that. I have very brilliant people who work with me. We've got a 480 volt small horsepower motor, and I can turn it on. All right. So what we're going to do, you'll notice that my sludge that I'm going to pour in there is not green or brown, okay, or black. All right. It's red. We're going to pour our sludge in the tank. Let it all go to the bottom, which it did. And now the goal is, this is your tank, okay? I'm going to let everybody can come up as soon as I'm done. I'll try and be brief, okay? And you come and look at it. Now there's a sweet spot. But the goal is, 100% uniformity. What do you think? They get it? Okay. Thank you for your time.